All right, ICC Passage number 6. In terms of the passage itself, the only thing that I highlighted was that liquid water has got an average of 3.4 hydrogen bonds per molecule, and that upon freezing, it can participate in 4 hydrogen bonds. Besides that, it's all stuff that we already know. If the colligative property stuff is unfamiliar to you now, we're actually going to go over it later today in class. January 22nd is today's date. So we're going to go over it later today in class. But one of the deals with colligative properties is that there's two things. One, it depends on how many ions are dissolved in the solution, not what the ion actually is. And two, dissolving something in water tends to extend the liquid phase of water. So that can imply a couple of different things, like lower vapor pressure, higher boiling point, lower freezing point, etc., etc. So, question number 1 says the solid lattice of diamond has a tetrahedral arrangement of atoms similar to that of ice. The hydrogen bonds and the covalent bonds of ice are replaced by which types of bonds in diamond? So, for diamonds, we know what a diamond is, right? It's carbon that's spent a very long time coming into this particular tetrahedral arrangement, but most importantly, we know that diamonds are made of pure carbon. So, carbon only forms covalent bonds. As for hydrogen bonding, can we have a hydrogen bond with a carbon? Nope, it's not fun. We need F, O, or N, which we don't have. So hydrogen bonds is out. A is out. As for ionic bonds and covalent bonds, okay, C is also out because of hydrogen bonds. For B, carbon almost never forms ionic bonds, so that one's out. And our best answer choice is D, covalent bonds only. 2 says the freezing of water is accompanied by an 8.3% increase in the volume that can cause water pipes to burst and rocks and concrete to crack. In addition to which of the following substances, or the addition of which of the following substances would be most effective in preventing the cracking of water-filled swimming pool during the winter? So this is a colligative property, right? We want to extend the liquid phase of water to prevent it from freezing, because when it freezes, it expands, and it's going to crack the pipes. So that depends on what? The Van Hoff factor, I, which is a number representing how many ions something splits apart into. So we have NaCl, CaCl2, MgSO4, and sucrose, 6C6H12O6. So we want to know what's the Van Hoff factor for each one of these. NaCl is 2 because it breaks into Na plus, Cl minus. CaCl2 breaks into 2 Cl minus plus 1 Ca2 plus, giving you a Van Hoff factor of 3. MgSO4 has a Van Hoff factor of 2 because it breaks into an Mg2 plus and an SO4 2 minus. And sucrose, C6H12O6, anything that's not an ionic bond or any biological molecules always have a Van Hoff factor of 1. So which one produces the greatest number of ions when you dissolve it? That would be answer choice B, calcium chloride. 2 says at 355 Kelvin, the vapor pressure of pure water is 0.5 atmospheres. If 2.75 moles of ethylene glycol were added to 1 liter of water at 355 Kelvin, what would be the resulting vapor pressure from the above solution? So this is also one we're going to go over in class today, but if we look over to equation 1 in the passage, which we didn't highlight, right, because it was an equation, it was a figure, it says that the change in pressure is equal to negative the X, where X is the mole fraction of the solute, P naught being the initial vapor pressure. So we want to know the mole fraction of ethylene glycol in water. It told us that there were 2.75 moles of ethylene glycol. How do we figure out the mole fraction? So this is a fact that if you didn't know already, it's probably going to sound really weird to you. But it's true. Water has a concentration in water of 55.5 molar, which doesn't make any sense, right? But if we look at it, we know that the density of pure water is what? 1 gram per milliliter, right? So if there's 1 gram per mil of water, then there's 1,000 grams per liter of water, right? So if in 1 liter of water, we want moles over liters for molarity, there's 1,000 grams of water for every liter of water. At 18 grams per mole, we actually wind up with 55.5 molar. That's how many moles of H2O are in a liter of pure liquid H2O. So the mole fraction of the solute, we know that we added 2.75, approximately 3 moles of ethylene glycol, or solute, over that 3 moles plus water, 55.5 moles. So the 55.5 plus 3 is going to give us 58.5. So we have 3 over 58.5, giving us approximately 1 over 20, or 0.2, or 0.05, sorry. So, using our formula, we know that change in vapor pressure is going to be equal to negative 0.05 times the original pressure, which was 0.500, giving us negative 0.025 as the change in vapor pressure. Our initial pressure was 0.5 atms, so minus 0.025 is going to give us our answer, 0.475 atmosphere. Answer choice B. 4 says, of the following, which substance is expected to have the highest heat of vaporization? Well, heat of vaporization is how much energy it takes to bring the molecules of that substance from a liquid to a gas, right? So that's going to take more energy depending on what? Intermolecular forces. The more these molecules hold hands, the higher the intermolecular forces between the molecules, the harder it's going to be to break those intermolecular bonds and bring it up into the gas phase. So, out of those we have water, ammonia, methane, and carbon dioxide. We can immediately knock off CO2 and methane, right? Why? Because they're nonpolar. They're nonpolar. Water and ammonia are polar. So not only are water and ammonia polar, but they can hydrogen bond. So between the two of them, which one can hydrogen bond more? We know that ammonia looks like this. So we draw our circle around a lone pair of electrons, the H and the N, and we can see that we can form 1 hydrogen bond. Water, we learned in the passage, can form 2. So water's got a greater hydrogen bonding capability. It's got the strongest intermolecular forces. Therefore, we should get answer choice A. 5 says the physical properties of ice make it particularly suitable as a medium for ice skating. However, dry ice, solid CO2, could not function as a surface for ice skating, even under conditions where it doesn't sublime. Which of the following conditions, statements best explains this? So let's take a look at A and C, right? It says, although CO2 rearranges into tetrahedral lattice upon freezing, it lacks the thermal stability of solid water. So do we know that CO2 arranges into a tetrahedral lattice? Nope. It doesn't have hydrogen bonding capability, so I wouldn't suspect that it would. C, the freezing of dry ice is depressed under increased pressure, whereas that of water is not. So we know that why is water special? Because its phase diagram looks like this, with a slightly negative slope. So that means that as the pressure increases, as we increase the pressure, the temperature at which the solid-liquid interface is going to happen, which is what we need for ice skating, is going to go down. So we get a lower freezing point as we increase the pressure. Now, for most things, we get a phase diagram that looks like this, with a slightly positive slope. CO2 is no exception, so as we increase the pressure, the freezing point of dry ice is not depressed, it's actually raised. So A and C are out. D is okay, but it talks about the solid gas. It talks about the solid gas interface, sublimation deposition, as opposed to the liquid gas, or liquid solid, which is what we need for ice skating. So D is out. That leaves us only with our answer choice B, that water is depressed under increased pressure, whereas that of dry ice is elevated. Finally, question 6 says, this is a hard one. This is a 117-gram sample of NaCl is dissolved in 1 kilogram of water at 1 atmosphere. As a result, the liquid phase of salt water is colligatively extended by a total of how many degrees compared to that of liquid pure water. So we have a certain concentration of NaCl, right? And we want to know by how much the boiling point and the freezing point are extended. So there are two formulas that we're going to learn in today's class, the change in boiling point and the change in freezing point, that we could use to solve this. But that would be a really long way to do it. We don't need it. All we need to do is look at figure 1. So if we look at figure 1, this is, well, first, let's figure out what we're dealing with. That needs two, this is, figure 1 talks about 2 molal NaCl. And if we do the math, figure out that 117 gram sample, NaCl, which has a molecular weight of Na is 23, Cl is 35.45, so 58, about 58 grams per mole. You're going to find out that we actually have 2 moles of NaCl for every 1 kilogram of H2O. In other words, 2 molal salt water. So if we check out 1, this is the pure H2O right here. So we want to know by how much the boiling point and the freezing point were colligatively extended. So we'll take our normal pressure, and this difference right here, and this difference right here are the two that we want to look at. So bringing it down, that translates to the freezing point going from 0 to negative 7.4, and the boiling point going from 100 to 102. So this 7.4 is approximately 8. This is 2 degrees. All told, that gives us a 10-degree extension on the liquid phase. Answer choice C. Once again, that was, we went 8 degrees lower for freezing point, 2 degrees higher for boiling point.